Okay, when we think of electricity, you think of electrons flowing through a wire or a device plugged in to a power source, be it a battery or like power coming out of the wall outlet. So electrons flowing through a wire, we call that a current, electrical current. The symbol for electrical current is I. And here's the equation for it. It's Q over T. I don't know why they put triangles. Okay, but that's how it look on your equation sheet. Okay, Q is the charge, the amount of really electrons in coulombs over the time. So the amount of coulombs that passes by a given point in a given time. So that'd be coulombs per second. Okay? Another unit equivalent to a coulomb per second is an amp. So 1 amp by capital A, designated by capital A, is the unit of charge. It's the same as a coulomb per second, capital C over lowercase s. Okay, the amount of current that's flowing through a wire depends on or through anything, depends on the type of material that's carrying the current and the electrical potential difference, the voltage on either end of the wire. We'll get to that later. Okay, so they present a pretty cool analogy here. Think of a pipe with water flowing through it. So the pipe is like a wire, okay? And the water in the pipe is like the electrons flowing through the wire. Now this water in the pipe will not flow forward unless it has potential energy. So if the pipe drops, let's say to this level, the water will now be flowing faster than it was in the higher level. It has more pressure behind it, if you want to think of it this way. So this is how the pressure is built up in water that we get in our homes. Either it's pumped at the water company, giving it that energy, or it's falling from a water tower high up over the ground. So when the water gets to the ground level, it has that high pressure. So how does that relate to a wire and electrons? Well, when you connect something to the wire to a battery, here's the terminals of a battery, let's say. This is a high potential, the positive, and the negative is a low potential, actually zero potential. So this provides the work to push the electrons through the wire. The pump or the height of the water tower provides the energy to push the water through the pipe. So we can think of a battery as an electron pump. It's doing work in pushing the electrons through the battery, giving them from where they return to the battery low potential if there's devices like a light bulb or something that's using the energy wired to the circuit. So the electrons give off some of their energy to the appliances that are hooked into the wire circuit, and the electrons returned to the battery low potential energy electrons, and the battery pumps them back up, much like when our water is used, is pumped back up to the water tower. So I already did this with you. I equals Q over T, coulombs over seconds, which is the same thing as an amp. Really, amp is a short abbreviation for amperes. Ampere was a scientist who was an early pioneer with electrical discoveries. Early on, when people were first studying electricity, they thought that current was positive particles moving through the wire. I mean, they took a guess, 50-50 chance. They knew there were positive and negative charges, and they just figured, well, let's say positive charges are moving through the wire. They didn't know anything about atoms yet. Okay, we know that protons don't flow through wires. The protons are in the nucleus. It's the stripped off electrons that flow through the wire in electrical current. So this is called conventional current because this is what they thought a long 200 years ago, or whatever it is. So conventional current is positive particles flowing through a wire. Okay, we now know. So conventional current is the movement of positive charge, even though it's really negative charges that are flowing. So it's really opposite to the direction of the electron flow. So if I have I going this way, conventional current, really the electrons are flowing through the wire this way. Okay, so you're going to have to do that mental flip. Doesn't really matter because whether it's electrons or positive particles flowing the opposite direction, it has the same effect. So this is a schematic drawing of a very simple circuit. Here we have the symbol for a battery. A battery simply two parallel lines connected to a wire. The longer line is positive terminal, and the shorter line is the negative terminal, always. Okay, right here is a switch that looks like a door, an architect layout of a structure. So when the door is open, the electricity can't flow through the circuit. So when the switch is closed, we have the circuit flowing electricity through it. So look, conventional current I shows it coming out of the plus. Well, it really doesn't do that. It's really electrons flowing the other way through the circuit. Okay, and then here's a symbol for a light bulb, something that uses the energy of the electricity and changes it into some other form of energy, in this case, light and heat. So there you have a very simple circuit. The rest of it is the wire, a conductor that readily lets current, electrical current through it. So these problems are really simple. What is electrical current passing through a heating coil of a hot plate? If 36 coulombs of charge, okay, that's Q, passes through in 9 seconds. So basically, I don't know, you picked the only equation I've given you so far. So that'd be 36 divided by 9. And so that would be 4 amps. Okay, here's another problem. A current of 0.6 amps, so that's I, through a resistor. A resistor is something that uses the energy of the electrons as it flows through them. Any device that you hook up to the wire that uses electricity is a resistor. So how much electric charge will flow through it? So I'm looking for Q in 3 minutes. You can't use minutes, you gotta use seconds. So let's see, 60 times 3 is 180 seconds. So you should be able to solve this. I equals Q over T. Q would therefore equal IT, which is 180 times 0.6, which calculates out to 108 coulombs. I could change that to electrons that are flowing by, but that was at the very beginning chapter on electrostatics. I won't do that. So you should be able to do this one. How long a time would it take for 250 coulombs, okay, that's charge, to pass through a wire if the current is 0.5 amps? So that's I equals Q over T. IT cross multiply equals Q. So T equals Q over I. So that'd be 250 over 0.5. 250 over 1/2 is 2 times 250 is 500 seconds it would take. So you guys can find this one out. And then just use this QR code, scan it to find the answer. Okay, you can simply, with what I just taught you, you can use this QR code, find the answer if you want. So once again, these batteries have a positive terminal and a negative terminal, that little depression on the bottom. So inside the battery, chemical reactions occur that energize low energy electrons and turn them into higher energy electrons. So high UE electrons from low energy electrons. So they bring the battery by chemical energy, turns low potential or low voltage to high voltage. Okay, so, or potential if you want to call that. So think of a battery as a pump that, like in the water company, that pumps the water, that comes back to it and energizes it, pressurizes it. In this case, gives higher energy to the electrons. Okay, they call it an escalator. I call it a pump. Okay, resistance R. Resistance is the just what it says. It's resistance to the flow of current. So think of a pipe. If it had a a plate in it with holes, like a colander, a sieve or something, the water would resist the water. It would resist the flow of water through there. Okay, it would probably slow down. It would make less, the water would lose some energy. Okay? On this side, the water would lose some energy as it goes through that. Resistor in electrical terms is in the wire. Let's magnify the molecules or the atoms in the wire are arranged in such a way that they absorb some of the energy as the electrons pass through. They absorb some of that energy and slow down the electrons from where they were. So the I decreases as the resistance increases. Pretty simple. Now, copper wires have very low resistance unless it's very thin, unless the wire is very thin and very long. Then the wire will get heated up and might melt. So electrical resistance is measured in ohms. Symbol for ohms is this Greek symbol omega. So there's two factors that affect the current. Resistance and voltage. Okay, obviously the bigger the voltage, the more work can be done to push these electrons from low energy to high energy. So a higher voltage battery has a bigger current coming through it for a given circuit. So I is directly proportional to the voltage. So the higher the voltage, the higher the current. So if you think of the water analogy in the pipe, the more powerful the pump is, or the higher up the water tower is, the faster the water will flow through the pipes on the ground. And we just said that the current is inversely proportional to the resistance. The bigger the resistance of the conductor, the smaller the current running through it. Okay, here's the equation for the relationship between current, voltage across the conductor, and the resistance of the conductor. I like to write it like delta V equals IR. Now they're getting lazy. They're not writing the triangle anymore, which is fine. Okay, so the units for volt potential is volts or joules per coulomb. The units for current is amp, and the units for resistance is ohms. So an amp is really another way of seeing. An amp, we said, is a coulomb per second, but it's also a volt per ohm. Now, if you applied voltage versus current, the slope of the voltage over current graph would be resistance, right? E equals IR. Okay, so if the resistor is said to be ohmic, it follows Ohm's law. It follows Ohm's law. And you have a straight line. No matter where you take the slope, it'll be the same. So you slope up here, to slope down here, it'll be the same. Now for non-ohmic conductors, the resistance increases with increasing current because something happens inside the wire that makes it have a higher resistance. The more current flows through it, it gets hot, and those molecules start forming a better blockage of the current. So non-ohmic conductors do not follow Ohm's law precisely, but you still get the relationship of an upward curve. So these are exceedingly easy. Calculate the current in a wire, a resistance, and potential difference across the wire is 18 volts. So V equals IR. I'm looking for the current. And so 18 divided by 4.5 is equal to 4 amps again. So again, incredibly easy. How much voltage will you have on either side of a wire if 0.3 current is running through the wire and the resistance of the wire is 120 ohms. Okay, so V equals IR. I don't have to rearrange that. 0.3 times 120. That would be, let's see, 360, but move the decimal point, so that'd be 36 volts. Okay, another easy one. What is the resistance of a coiled wire when 12 volts as voltage across the rheostat coil is, and the current 0.04. So V equals IR. We're looking for R. So divide by I. So I got 12 divided by 0.04. 12 divided by 4 is 3. And then 1, 2. So that's going to be 300 ohms. Okay, you can do this one. Check the QR code. Same with this one. Again, same with this one. Check the QR code. Okay, so electrical power devices that are hooked onto circuits will use the energy of electrons flowing through them to do work. And the more powerful things plugged into a circuit will use more energy in a given amount of time and do more work because of that in the same amount of time. So power, the old equation for power is work over time. And work by, when we talked about potential, work is Q times delta V. Okay, so the charge times the potential that's moving through. And then we can just substitute this for that, work for QV, and so we get this equation right here. And because I equals QT, we can substitute the I in for the Q over T. And so we get this equation, which will be on your equation sheet. So just from the equation, you can see that the power is directly proportional to the current running through the device. And the power is also directly proportional to the voltage across the current. So what happens if current is decreased? Power increases. What happens if voltage is decreased? the power would decrease, because power and voltage are also directly proportional. So here's the equation for power, electrical power. What's the units for electrical power? What units for I is amps, or coulombs per second, right? The unit for voltage is volt, which is a joule per coulomb. So the units turn out to be a joule per second when you multiply those, which is a watt. Okay, so the units for electrical power is just like the unit for normal power we were talking about first semester. Now, if you don't have the I, if you don't have the current, but you know the resistance of the thing that's using electrical energy in the circuit, if you know its resistance but you don't know the current running through it, you can use a variation of that equation. It's right here. P equals V squared over R, where V is the voltage across the resistor which is using the electrical energy in the circuit. R is the resistance of the resistor that's using the electrical energy in the circuit. And P again is power. So how do I get that? Well, if I don't have I know I equals VR. I substitute V over R for the I. And so now I get V squared over R. And you can do the same thing. P equals IV. If you don't have V, if you don't have the voltage, the potential difference across the resistor, just use Ohm's law, because V equals IR, and substitute that in for the V that you don't have. And you'll get P equals I times IR, which is I squared R. So there's yet another equation for power. These equations are really simple again. Okay, what is the power used by a light bulb? Power consumption, how much electrical power does it use when connected across a 120 volt power supply? Okay, that's like plugged into the wall. That's what the voltage coming out of the wall is. It's 240 if it's a dryer, but for normal appliances it's 120. So simple, P equals IV. I'm looking for P. So 0.5 times 120 is half of 120 is 60 watts or joules per second. Okay, next one. An electric motor has a resistance of 17 ohms. So that's R. Find the power delivered by a 6-volt battery. That's the voltage. So P equals IV. But I don't have I. So I'll substitute P equals IR. I'll substitute this in there. So P equals V squared over R. Okay, and so it's 6 squared over 17 is what the power is. And I get 2.1 watts. That's the wattage that the motor is using. So here we have a current going through the elements in an electric oven. The resistance is 20 ohms. What's the power used by the oven? So P equals IV, but I don't have I. So, wait, I have I don't have V. So V equals IR, so I'll substitute that in for this. So this is I times IR, I squared R. So this would be 4.5 squared times the resistance. And I get 405 watts. 405 watts. Okay, you can do this one based on what I just did as examples. Look at the scan the QR code to find the answer. Same with this one. Same with this one. Same with this one. Okay, so I showed you a very simple circuit diagram earlier in this study guide. And let's learn some symbols. A new symbol. Resistors modify the current in a circuit. And if you ever opened up an electronic device that wasn't just on a computer chip, run by computer chips, you would see these little things in the circuit board. These are called resistors, and the symbol for resistor is this little zigzaggy thing, as is shown right here. Okay, so let's draw a simple circuit. It's a 9-volt battery. Okay, it doesn't matter where you start. I'll put 9 volts next to it. 3 ohm resistor. Doesn't really matter where you put it. I like to make the wires like a rectangle. Okay, there's a resistor, which is 3 ohms. Okay, you don't have to put a triangle anymore because it's always going to mean potential difference. So they continue to ask, what is the magnitude and direction of the current? Well, this is the plus n because it's longer. So the conventional current comes that way, out of positive, even though we know electrons flow out negative, but we still adhere to this conventional current idea. So V equals IR. 9 equals, we're looking for the current, which is I. R is 3. So I equals 9/3 is 3 coulombs per second, or amps. Okay, here's 2 different kinds of simple circuits. I added another resistor to the one I just had. Okay, so I could put it right in line with it, or I can pile them up so that they're parallel to each other in a little section. So when they're lined up like cars on a train track, we call that those resistors are wired in series. When they're wired in series, there's only one way for the current to go. There's only one loop for the current to go from plus to minus back to the battery. Okay, and that is the way I just showed. There's only one road for electricity to go, for the current. Now, again, I'm talking about I, whereas really the electrons would be going from the minus to the plus, but whatever. Okay, so now if there's 2 ways for the current to go back, or more, there can be more. for the current to go back to the battery. If there's two ways, two paths, then those circuits, those resistors are wired in parallel. So I'm going to just follow this. Oh, the current can go through this thing, or it could go through up here. Oops. It can go through here like this, and then down through this one, and then back around. Let me ask you, what if I had this situation? Here's R1, here's R2, here's the battery right here. Okay, now, if you say these aren't parallel or in series, a lot of people think they're in parallel because look, this line is parallel to this line. Well, that's not how you do it. If you see, here's the current. If the current goes through that, it must be the same current going through there, right? There's no alternate way. So this is in series. Those are R1 and R2 are wired in series. Or we say this is a series circuit. And what if it looks like this? Let's put the battery up here. Here's R1, here's R2, here's the voltage source, the battery. Okay, so here's the plus, here's the minus. So is this in parallel or in series? Well, you can see that the current could go this way, the conventional current, or it could go this way in this loop. So since there's two paths for it to, the current, conventional current to move through, this is in parallel. These two guides are wired in parallel, these two resistors. Okay, so take the test. See if there's alternate paths. This one, you could go this way, and the current could go that way from plus to minus, or it could go this way, this path, or it could even go all you have to do is find more than one. Okay, how about this one? Obviously these guys, this second one, the only path for the electrons to travel or the conventional current to go is that one. So that's in this one's in series. Because this has alternate paths on the left one, this is in parallel. The resistors are wired in parallel. Okay, this slide is showing that when we start to do circuit problems, we're going to have to use Ohm's law, but we have to have the total resistance to use Ohm's law. And the total resistance they call the equivalent resistance. I don't know why they just don't do sigma R, but I'll follow their rule. Okay, so they rewrite this, or they visualize it like this, where the two become one, so that they can figure out the current if they have the voltage. Now, we're going to follow the rules on how you can find the equivalent resistance and how that allows us to find the current running through the circuit. Now, when the resistors are in series, there's only one path for the current to go through. And we can say that I don't care what the resistors are, one bigger than the other, it doesn't matter. The current will be the same through each resistor if they're in series, okay? So if it's in series circuit, we can say that I equals the current running through anywhere in that circuit, in that loop that the current's going through. Okay, so I1 would be the current going through R1. I2 would be the current going through R2. But those aren't all the currents, if they're in series, have to equal each other. So here's the rule. So the total current, I'll just call it IT. Total current is I1, the same as the current going through R1 or R2, or the battery for that matter. Okay, so there we have that rule. Now the voltage. So if that's VT for total voltage, this voltage, no, this little symbol is showing a voltmeter. A voltmeter. So what you do is you take this meter and you put its two wires across the resistors. We'll do that in lab. So what we can say that there's a voltage drop across each resistor. And I'm not saying those are equal, but I'm saying that V1, the sum of those voltage drops, is the total voltage across both of them. I mean, you know, if I put a voltmeter across both of them, that'd be the total voltage. Now, if I put a voltmeter here, what would that reading be? Is there a voltage drop right there? Is it going through a resistor? No. So this would read nothing. There wouldn't be any difference in the voltage, the potential energy of electrons there and there. But there is a drop from here to there whenever you have a resistor. Now, the wire has a very small resistance, but it's negligible. So this is true for in series. I'm just talking about in series circuits, where the resistors are wired only in series. Okay, so there's that equation where VT, the voltage reading over the first one, the voltage reading over the second one. This is called a voltmeter. A voltmeter is the device I'm drawing right there. We'll use one in lab. Okay, so let's put what we just said together here. So if VT is the total voltage equals the sum of the voltage drops, and also we know IT equals I1 equals I2, so I know all the I's are the same. So if I use Ohm's law, V equals IR, I would get I R total equals I1, R1 equals I2, etc. Okay, I'm just doing Ohm's law for each one of these voltages. Okay, well, because I is the same everywhere, it cancels out. Okay, the I is the same everywhere, so it's going to just cancel out on all sides. And so rewriting that, we got R equivalent, I call it equivalent resistance, total resistance. Okay, so I'll flip around and do that. So this is the new rule. The total resistance of the system is the sum of the resistances, only if they're in series. Okay, this is only if we're talking about things in series. Okay, so only series circuits. So you should know these three rules for series. The ones I circled in blue. So let's do an actual problem here. What is the equivalent resistance? So that's easy. They're in series, right? So RT is R1 plus R2. 5 plus 7 is 12 ohms. So here they're showing you what I just did. You should know that whenever we add resistance in series, it always increases the total resistance because of this rule. Okay, so what is the total current? IT. Okay, so it's the same anywhere because it's in series. So VT equals IT, RT. Well, let's find RT. Because they're in series, I'm just going to add them. 5 plus 7 is 12 times IT equals total voltage or potential difference is 9 volts. So IT equals 9 divided by 12. That'd be 3/4, which is 0.75 amps. And here you see they did what I just did. Okay, so here we have the same problem. What is the voltage drop across R1? So what they're basically asking is, what is the voltage reading across this? Now it's called a drop because it's subtracting. It's taking away voltage from the 9-volt battery, which is so what is voltage drop across R1? So I'm just going to do V equals IR. Okay, I have the I from what I just did, I think was 0.75, right? Amps, because it's 0.75 wherever you are. And then R1 is 5. So V1 is 3/4 times 5. 15/4. 15/4. So that'd be 3.75 volts. Actually negative because it's a drop. So you should be able to do this one because it's the same idea. Voltage drop over R2. Use Ohm's law. So let's plug in what we know. I2 was 0.75 from before. R2 is 7. So V2 comes out to be a negative 0.75 times 7. which is 5.25. It's negative because it's a voltage drop. Now, if you recall, V1 was 3.75. And V2, we just found out was negative 5.25. If you added those, if you add negative 3.75 plus negative 5.25, you're going to get negative 9 volts. So that's what we expect. There is a total drop in the voltage equal to the voltage, total voltage, which is 9. So you can just say that if you want to, VT equals V1 plus V2 and disregard the negatives on the voltage readings. All I have to do is flip the terminals around and it comes out 3.75. So the sign really doesn't matter. How much power is used by R1? Okay, well, I have the current, total current, or I1 is 0.75 amps. We already did that. So P equals IV. I had the voltage drop. So the current running through R1 is the same running anywhere throughout the circuit is 0.75. The voltage drop was 3.75 volts. Disregard the negative. So I get 2.81 watts for the power being used by the 5 ohm resistor. Okay, so they did it. If you're going to use, be sure that the voltage drop across the resistor is used, not VT, when you're solving for P1. Okay? So here they're asking for the power used by other resistor. It's the same exact thing. Okay, so you can follow the work. And you get 3.94 watts. I would just done this right here. P equals IV. Simplest equation. But you could use either of the other two ones. I don't know why. Oh, this is a totally fresh battery. We can say P equals IV. So 0.75 was the current, right? And the total voltage is 9 volts. So 3/4 times 9 is 6.75 watts. Okay, so that battery is producing 6.75 watts or 6.75 joules per second to run this circuit. So check this QR code to find the answer for this. Same with this. Same with this. Same with this. Same with this. Okay, so now we're going to do parallel circuits, the same thing that we do with series circuits. What happens to the circuit on the right? Okay, conventional current. What happens to the current in the circuit? So it's going to split up. It's going to go that way and circle around like this, back to the battery, and it's going to go this way, make another loop and go back to the battery. So it's parallel circuits. So we got two different currents. The current's not going to be the same through R1, R2 unless they're identical resistors, equal ohms, but usually they aren't. Okay. So what do you think happens to the voltage? So we got V1 here, and the voltage over here is V2. And the voltage across the battery is V total. Now for parallel circuits, this is true. Vt equals V1 equals V2, except these are negative and this is positive, and but we just disregard the negatives, like I said. Okay, so this is much like the IT equals I1 equals I2 rule for series, so don't get it mixed up. So here, just what I just said. I'm just going to circle the rules that apply. Okay. First, the current splits off into whatever number of resistors in parallel. And they have to add up to be IT. So that's the first rule for parallel circuits. The second rule for parallel circuits is right here hiding. So if you have three resistors, the voltage in parallel, the voltage will be the same across each one of those, and they'll equal the total voltage across the whole branch, or the total voltage of the battery. Okay, so right here, all they're doing is verifying this rule right here, which I won't derive it for you. But for resistances, the rule for parallel resistances is that 1 over RT equals 1 over R1 plus 1 over R2, etc. Okay, so they're asking an important question. If you add more resistors in parallel, what will happen to the resistance of the circuit? Actually, the total resistance of the circuit. It decreases. Now, you can just plug in numbers for yourself and see if that's true. So let's just do that. Let's say let's say R1 equals 2 ohms. Let's say all of them equal. R2 equals 2 ohms. R3 equals 2 ohms. And then I go add R4 to it. Okay, if you only had these three, what is RT equal? Well, let's use this equation. 1 over RT is equal to 1 over 2 plus 1 over 2 plus 1 over 2. That equals 3 halves. But that's 1 over RT. So RT equals inverse 2/3, right? You gotta flip it around if you want RT. So 2/3 ohms. So what if I add another one? Okay, so 1 over RT equals 1 over 2 plus 1 over 2 plus 1 over 2 plus another 1 over 2, R4. So that'd be 4 halves, or 2. So flip it around, RT, the new RT would be, by adding just one more resistor, would be 1 half. Okay, 1/2 is smaller than 2/3. Okay, so adding resistors makes the total resistance decreases in parallel circuit. When adding resistors, but in series circuits it would just increase, because in series circuits, if you add, because it's not inverse idea, it would increase RT. They're just verifying what I just said. I did check the math out. Okay, so let's do some actual problems. What's the equivalent resistance of the circuit? Okay, so RT is equal to 1, well, be careful, 1 over, this is in parallel, so 1 over RT equals 1 over R1 plus inverse R2. So 1 over RT equals 112 plus 1/6. Okay, I could do common denominators, or I could use my calculator. I'm just going to do common denominators. So this equals 1 plus 2 is 3 12s. So RT, that's 1 over RT. RT, or REQ, is 12/3 equals 4 ohms. So I could rewrite this like this. As 1 resistor, 4 ohms. And I could RT. So instead of this mess, I could put it like that. Okay, so they just did it. They just did what I showed you. They actually did common denominators, but you can do this on your calculator without doing any math. So my answer would be 16 volts, because that's what the total voltage is. My answer, they got it. What's the voltage drop across R2? Same thing. Okay, if I put a voltmeter over here, it would read the same as a voltmeter over here, as a voltmeter over here, as a voltmeter over here. But what would a voltmeter here read? That would read 0, because there's no difference in the energy of the electrons on either terminal of that voltmeter. There's no potential difference. You can try that in lab. So the total current generated by the battery is IT. I have VT, that's 16 volts. And I have RT, which we found before, as 4. So IT equals 16 divided by 4 equals 4 amps, or coulombs per second. Okay, so sorry, I worked this out already. So where's the current through R1? So I'm looking for I1. Well, I know V1 is the same as V2 because they're in parallel. And the resistance is given as 12. So I'm going to use Ohm's law, plug in those values 16 is over 12 is 1.33 amps. And that's what they got here. So if I were to ask you how much current goes through the 6 ohm R2, all you have to do is take the total current, which is 4 amps, and subtract 1.33 from it. Or you could do the same thing we just did. Was 1.3. So that's what they're asking. So what is the current through R2? So I know V2 is equal to 16 VT because they're in parallel. Okay, so what is the current through R2? So Ohm's law again. So I2 equals V2 over R2 equals 16 over 6. I2 equals the total current minus I1. Total current was 4. And I1, 1.33. And so 4 minus 1.33 is 2.66, which I rounded up. So I could have done it that way. What? Okay, so you can see they solved that 2.67, really. You're right. Or they could have done this way like I did, showing you that IT is the sum of I1 plus I2 if the things are in parallel. Okay, I really think I need to do this. Just set it up for you. So power used up by resistor 1 would be, I already have everything I need. I have I already found the I, and I have the voltage, which is the same as the total voltage. Okay, so I'll let you look at the next answer for that. The next slide shows it. So they used a different equation because they used V and R. Okay, but I could just easily use P equals IV. Okay, so P equals the I through 1 is 1.33. And the V is 16. So 1.33 times 16 is the same thing, 21.3 watts. That's what I would have done. But, and you could have done the other one as well. There's 3 power equations. Pick the easiest. Same thing. As you can see, they're using that. Of course, I would use P equals IV. The power running through the second resistor is I2 is 2.67, and the total voltage is 16 volts. So I get 42.7 watts. Same answer. Okay, again, P equals IV. The total current was 4. The voltage is 16. So 4 times 16 is 64, I think, watts. So they finally used the simplest equation. Well, I'm assuming there's no resistance in the battery. As the battery runs down, it might say 16 volts, but because of its internal resistance, it's less than 16 volts. But we're not dealing with that. Okay, so please try these. Check the QR codes. This one, these are all the same thing. All the same thing. Whoa, this is a different one. This is a combination circuit. We got two things in parallel, and to those two resistors, we have wired a third resistor in series. So what is the total current in this circuit? This is trickier. So first of all, you gotta find RT. So let's think this out. So let's find RT here. Then I had this R. So let's do it this way. RT with 1 and 2. And then I'll find RT 1, 2, and 3 with them all together. So first of all, this is going to be R1. Let's call this RT 1, 2. This will be R3. Then I'll write it like this, all together as RT 1, 2, 3. Okay, anyway, that's how I'm going to find the current, the total current. Okay, so let's find RT 1, 2. 1 over RT equals 1 over R1 plus 1 over R2. So 1 over RT equals 1 over 3 plus 1 over 6. So if I use common denominators, but you can use your calculator, I get 1 over RT equals 2 plus 1, 3, 6. I can add these if I have a common denominator. And so RT 1, 2 is equal to, flip it around, 6/3 or 2 ohms. Okay, so this part right here is 2 ohms. Now, R3 is 4 ohms from what was given. So what is RT 1, 2, 3? So what is RT 1, 2, 3? Well, that equals 2 plus 4. The total resistance is 6 ohms. So now I can finally do Ohm's law to figure out what. So I'm going to use Ohm's law to find the total current. Okay, the total voltage of the battery voltage, 18. Total current times the total resistance is 6 ohms. So IT is 18 divided by 6 is 3 amps. Okay, so from the problem we just did, IT equals 3 amps. Okay, so they're asking for what is the voltage drop across R3. Okay, now be careful. IT comes out of here. It splits up into I1 and I2. But then it comes back together as IT again because charge is conserved. It doesn't disappear. So current is conserved. So we're trying to find voltage drop across R3. So V3, use Ohm's law. Okay, so V3 is what I'm looking for. I3 is IT for what I just told you, for reasons I just told you. This will be IT because when it came out of the two resistors in parallel, it went back to the original total current. So R3 is 4. So 4 times 3, so that'd be negative 12 volts. So I put down what we had in the last problem, what we found. So what is the current through R1? Well, V equals IR. So I1 equals V1 over R1. Well, I know what V1 is, right? Now be careful. V3 was what? We found that in the previous problem. That was 12 volts. We found that in the previous problem. VT is 18. Sorry about that error. So if V3 is 12, what's across here? V1, 2, if you want to do that. What's across these two, this is very important, is whatever adds up to 12 to be 18. So V12 plus V3 equals V total, because these guys, if I smush those together, plus this guy are in series. So V1 over 2, the voltage across this parallel pair of resistors has to add up to 12 to be the total of 18. So 12 equals 18. So V12 is equal to 6 volts. Okay, so 6 volts, but that means the voltage across V1 and the voltage across V2 had to be exactly what the voltage, total voltage across that piece is. Now, if this guy wasn't even there, that would equal the total voltage of 18 like we did in previous problems here. But that is there, so we can't do that. So I know that. So I know that V1 has equal V2 has equal V12, the total voltage across that pair of in parallel vector resistors. So I know that has equal 6 volts. So I can put 6 here, and then R1 is given as 3. So that comes out to 2 amps. Now, they're probably going to ask me what the current in R2 is. And that has to add up to the current in R1 to be the total current. I bet that's what they're going to ask me next. So, what if I ask you, what is I1? I'm sorry, I just found what I1 is. What if I ask you, what is I2? Well, because what I showed you up here, how this current broke up, how I total breaks up into I1 and I2. I can say I1 plus I2 equals IT. And I have I1 already. I solved it. It has 2 amps. And I know the total current is 3. So I can solve for I2 is equal to 1 amp. Okay, so all kinds of things I can ask you there. So this is a chain of questions for this circuit. So let's first find RT. Okay, equivalent resistance. First of all, I would jam these together because you would just add them when they're in series. So R1, 2 is equal to 18 ohms. 10 plus 8. Okay, and then this is R3. So the 18 ohms right here and the 6 ohms here are in parallel. So 1 over RT is 1 over R12 plus 1 over R3 because they're in parallel. So 1 over 18 plus 1 over 6 equals 1 over the equivalent resistance. And let's get common denominators. And so this adds up to 1 plus 3 on the top is 4/18. So RT is, flip these, 18 over 4, which comes out to 4.5 ohms. Okay, next, let's find the current from the battery. That'd be the total current. So that's kind of easy. VT, use Ohm's law. So 9 equals I times 4.5. I equals 9 divided by 4.5, which is equal to 2 amps. Next, we're looking for the current running through R3, which we'll call I3. Okay, so I'm going to use Ohm's law again. Okay, the voltage over across R3, the potential difference is the same as the voltage, the total voltage, because it's in parallel with the other set of resistors, and there's no resistor in series outside this parallel section. So V3 is equal to VT, again because it's in parallel. I3 I'm looking for, R3 is 6, so I3 equals 9/6 is 3/2 is 1.5 amps. So next thing we're going to find is the current going through the first resistor, which I know is the same as the current going through the second resistor because they're in parallel. Okay, the easy way to do that, I think, is to look at this diagram. So here's IT, total current. It's going to split up into two parts. So it's going to split up into I3, which we just found. And I'll call this I1, which is the same thing as I2 because they're in series. So let's just write the equation. IT equals I1 plus I3. So IT is 2. I1 is what I'm looking for. And we just found I3 up here is 1.5. So I1 is equal to 0.5 amps. Let's do letter E now. What's the voltage drop across R2? So I'm going to put a voltmeter right over R2. And that's what I'm looking for, V2. So we're looking for V2. So we know that this total voltage right here, I'll call it 1, 2. We know that that is the same as this voltage, which is the same as the total voltage of the battery. And that's because this is in parallel with this set of resistors. In the parallel rule, if there's no other resistor in series with it, which there isn't, states that all those voltages are equal. So we know the total voltage is equal to 9 volts. Okay, so we know that because the 10 and the 8 are in series, we know those voltages have to add up to be V12. So V1 plus V2 has to equal V12. Okay, so that equals 9. And V1 equals I1 R1. And we found I1 as 0.5. And R1 is given as 10. So V1 is equal to 5 volts. So going back to here, 5 plus V2 equals 9. So V2 equals 4 volts. So the next thing they're going to ask us is, what's the power used by R3? So what do we know about R3? We know the resistance. We see what we know. Okay, we know the voltage. Resistance is 6. And I don't know the I, but that's okay because I can find the power from just R and V. Okay, so I, from Ohm's law, I equals the voltage over R. So this would be V over R. So we got is V squared over R for the power that resistor 3 is using. So that would be 9 squared over 6, which is 13.5 watts. They're going to end this series of questions with letter G. What is the current running through R1 in a time of 2 minutes? So in 2 minutes, how much current has run through R1? Okay, so if you remember, I equals Q over T. So I1 equals Q1 over the time. The time is 2 minutes, but you have to use seconds because that's time in an equation needs to be seconds. So 2 times 60 is, because there's 60 seconds in a minute, and they want in 2 minutes, so that'd be 120 seconds. I1, we already found to be 0.5 amps down here in letter D. So Q1 simply equals I1 times T, which is 120 times 0.5, which is 60 coulombs of charge have passed. Now we can change that to total number of electrons by, like we did in the previous chapter. So 60 coulombs. Coulombs electron. One electron is 1.6 e to the negative 19 coulombs. So I get 3.8 times 10 to the 20 electrons. Okay, I'm not going to have you do that again, but you should remember that from the beginning of this electricity chapter. Okay, here's another circuit diagram. You can see that these two guys are in parallel, and that parallel branch is in series with R3. So the first thing I really want to do is find RT, or the equivalent resistance. So they're asking me that way in letter F. So let's do that first. Okay, so before I can find RT, let's figure out what R12 is. Well, the combined resistance of just that part. Okay, well, the equation for parallel resistors, for the resistance of a parallel circuit part, is 1 over 1 R1 plus 1 over R2 equals 1 over the equivalent resistance of just that piece. So that equals 1 over 2 plus 1 over 3. Again, you can use your calculator. I just like using common denominators. Okay, so common. So let's multiply that like this. So we get 3 plus 2 is 5 over 6. So R12, total resistance of just that part, is equal to, flip it around, 6/5. Which comes out to 1.2 ohms. Okay, so RT would simply be what I just found plus R3, because this plus that, I mean, those two, that set of parallel resistors and this lone resistor R3 are in series. So I just flat out add them. So R12 is 1.2 and R3 is 4. So I get 5.2 ohms for the total resistance. So I just answered letter F. Okay, I think we can do letter A now. Just use Ohm's law. This time we have I3 given as 1 in the picture. R3 is also given. So the voltage across resistor 3 is 4 volts. Looks like we already did R12 right up here to the left. And that's 1.2 ohms. Just look to the left there. Okay, I think we can do letter C now. What's the voltage drop across this section right here? So if I put a voltmeter across these, what would that read? Well, R12, let's call that V1, comma 2. Well, if this R3 wasn't there, it would be the total resistance of the battery, which is not given. But R3 is there, so we can simply go Ohm's law on that. Okay, letter C. V equals IR. Okay, R12 I already have as 1.2. Okay, so what's important to see is that the current going through this entire thing, if I smush that down, here, let me show you. Okay, R1, 2, then R3. Okay, R3 was 4 ohms. And R12 is 1.2 ohms. And can you see that the current going through here, which I'm going to call I total, is equal to the current going through R3.